I am Dr. Akshay Ranjan Paul from India, the chair of the session 8. I welcome to all the participants and attendees joining this session. I welcome Professor Zhejiang from Korea Advanced Institute of Science and Technology, South Korea. Professor Chiang, am I audible to you?
Yeah.
Thank you.
Hello, everybody. Can I have the screen sharing? It is says it is enabled by the host. My screen sharing is enabled now. So can you let me share the screen?
Let me request the secretariat to please enable the screen sharing. Is anybody there to enable the screen sharing?
It's not working yet.
One minute, please. Is there anybody from Conference Secretariat, Dr. Harun?
All the presenters, keynote speakers, and
yes. Dr. Harun, this is Akshay. I request you to please enable the screen sharing for Professor Chiang of South Korea.
One keynote.
Just a minute.
Speech. And the keynote speech is presented by Professor Din from Zhejiang University, China.
Is it all right?
We have
Okay, now it's working.
Yes. Thank you.
Okay. Can everybody see my screen and hear my voice?
Yes, sir.
Okay. Good morning, everybody. My name is Zhang at ICEP Korea. So it's great pleasure to have the keynote speech in this conference. The title of my talk is Material Challenge for Current and Advanced Nuclear Power Systems. And I'm going to describe key issues and describe some of the material that we have developed for the advanced nuclear reactor system. This is the collected work of my students, many of my students involved in the project, developing the new alloys. Okay, so first of all, I assume that many of the countries participating in this conference do not have the nuclear power. But here is one of the biggest reasons why the nuclear should be one of the major electricity generation capacity in many of the countries, including the Southeast Korean and Southeast the Asia and the Eastern Korean countries. So here is the trend of global warming. So we know that the temperature of the globe is rising, and we see some of the famous pictures describing the reduction of the polar ice. So it has some problem for many of the animals, but also the humans are affected by the global warming. So we know that there are several substances that cause the global warming, like carbon dioxide, methane, and the nitrous oxide. And many of those sources, the global warming elements or substances are emitted by the power station and the transportation, and also industrial processes. All of those areas, the major part of this one actually can be substituted by the carbon-free electricity sources. So there is here is one of the graphs showing that the lifetime emission of greenhouse gases for the several different the sources of electricity. So we know that the coals are notorious for the carbon dioxide emission, and also even though natural gas is less than the coal, but they still emit substantial amount of carbon dioxide. which is surprising that even the solar photovoltaic have a quite significant amount of carbon dioxide emission because of the fabrication process of those cells. Even though the photovoltaic doesn't emit carbon dioxide, the fabrication process and also the disposal and removal of a photovoltaic involves a significant carbon dioxide emission. Compared to that, those biomass and the nuclear and the hydro relatively have a lower amount of carbon dioxide emission. Among them, the nuclear has the advantages that, as I said, this one, there is no greenhouse gas emission and no pollutant. And the density of the fuel is quite significant. There is a rough comparison of the amount of energy generated from the uranium fuel of 1 gram is equivalent of 3 tons of coal. So that's a huge difference. And also nuclear is everybody agrees that it's a very economical source of power generation. And also it's a very, very technologically intensive. So if any countries develop the nuclear power plant, it has to have a huge amount of the industrial and the science and technological the basis. And the related industry can be developed as one country developed the nuclear power, like the heavy equipment and the plant engineering, construction and the fuel and the non-distribution, and the many others, the industrial sectors are developing with the development of nuclear power. So this is worldwide statistics of nuclear power plant as of year 2018. So roughly 450 nuclear power plants are running, and around 50 or 60 nuclear power plants are under construction. And roughly around 30 countries are operating or constructing nuclear power plant worldwide. Here is the status of Korea. We have 21 so-called pressurized water reactors. That's a water-based reactor. And there are several different designs. And with them, around 14 of those reactor designs are Korean designed nuclear power plant, OPR 1000 and APR 1400. This one is basically the capacity of the power plant. 1400 megawatt is electricity capability is APR 1400. And we have 3 CANDU reactors utilizing heavy water reactors. And there are actually 4 APR 1400 is under construction. They are near completion. And there are another 4 reactors are on halted condition due to some situation. And we have 2 shutdown nuclear power. So overall, nuclear power is taking about 30% of electricity share in South Korea. So here is the structure of nuclear industry and the regulatory bodies. So-called this is Team Korea. And this is the structure of APR 1400 development program. So this is KHMP, they are the utility, and there is a KECO ENC, they are architect engineering, they are basically designer of the APR 1400. And the Turan heavy industry, this is one of the biggest equipment of manufacturer in the world. And Kaeri is Atomic Energy Research Institute. They are doing all kind of nuclear related R&D. And KPS, this is plant maintenance. And KEPCO NF is a nuclear fuel supplier. So we have completed the supply chain of nuclear power plant design, construction, and operation. And this one is constantly regulated by the Nuclear Korea Institute of Nuclear Safety, so-called the KINS. And on top of that, we have NSSC, that is a National Nuclear Safety Security Commission. So with this Team Korean effort, we actually exported 4 units of APR 1400 to the United Arab Emirates in year 2010. And the first unit of that one started construction in 2012 at the Baraka site. This is the location of the Baraka. And this is the city of Dubai, and this is the city of Abu Dhabi. So this one was completed in year 2018. That is on time, in budget. So this is the very important milestone acknowledged by the International Atomic Agency and the Nuclear Energy Agency of OECD. And they started commercial operation in the year 2021, and the next one will be also operating maybe next year. So this is the attainment of the 4 APR 1400 unit at the peroxide. In addition to that, we have submitted the design of APR 1400 to US NRC. This is basically the United States regulatory body, and then we submitted the document, and they approved the design of the APR 1400. This is actually very important milestone that the US never ever issued the design certificate for any other countries. So this is the first non-US design, the nuclear reactor design. So that is a significant acknowledgement of safety of APR 1400. So that is the overview of the Korean nuclear system, nuclear and nuclear structures. So this is a brief introduction of a nuclear power plant. Nuclear power plant is the plant that simply convert the nuclear energy produced by the fission of uranium-235, and eventually through the many steps of energy conversion, and eventually produce electricity. So the nuclear energy production part is called the nuclear steam supply system, and the electricity generation part is called the BOP system. So this is the entry press system, and this is the BOP system. So in the core of the entry press system, this one is called the closed coolant system or primary system of nuclear power plant. And in the primary system, in the center of that is the reactor pressure vessel. So in bottom here, you have the reactor fuel, and then you have the steam generator, and the steam is produced, and it goes to the BOP system. So the integrity of those the component, and also the material property change of those material used in these components are critical for the safe and reliable operation of a nuclear power plant. So in addition to that, currently the nuclear industry is interested in developing and deploying so-called small modular reactors, small size and modular type of reactors, so-called SMRs. And there are actually many different types of SMRs are being proposed and being developed. But one of the leading SMRs based on the water coolant system is the so-called NuScale system, that is a US design system. And this is ISMR that is designed in Korea. So they are under development. And then they are aiming for the highly reliable and longer life and the very economical nuclear power plant. But the size is small enough to be deployed in any other area when it is necessary. In addition to that, there are other type of reactors, SMRs are being developed. This one is using the other coolant than the water. Okay? So there are several different reactors utilizing liquid sodiums or liquid lead, or utilize high temperature helium or CO2 as a coolant. And one of the recent development is molten salt reactors. They're utilizing molten salt as a reactor coolant system, having some very interesting features of safety. Okay. So in those the advanced nuclear reactors, including the light water reactors or non-water based reactors, all of those the new designs are aiming for better efficiency. So to achieve a better efficiency, as everybody knows, you have to increase the temperature of your system. Right now, the current reactor is operating at somewhere around 320 degrees centigrade. But for the advanced reactors, your temperature will be somewhere around 550 to 900 degrees centigrade. And because of that, you should have the proper material that can have a high temperature strength and also the proper corrosive resistance at those temperatures. And also the coolants right now mostly it's water, but we have a variety of liquid metals like liquid sodium, liquid lead, or lead bismuth synthetics. And also you have the molten salt, there is a fluoride-based salt and chloride-based salt, and the SCO2, sulfuric CO2, and the heliums. And because of those, the various coolant and they are operating at the temperature, we are expecting that it will be significantly aggressive environment for the material. So you have to worry about the corrosion, and you have to figure out how to mitigate those corrosion or how to develop the better material, have a better corrosion resistance. That is also important because we are aiming for the lifetime of nuclear power plant from 40 years to extending to 60 to 80 years. And because of that, if you have the material within the reactor cores, that radiation damage of material will be much, much greater than the current version of a nuclear power plant. And in addition to that, because of the requirement of safety is ever increasing in many of the countries, so you should have the material should have higher reliability compared to the current materials. So if you consider all of those requirements, then this is the direction of advanced material for advanced nuclear reactor power plant. So basically, you should have a high temperature strength and grip. In addition to that, you should have also the enough ductility at all different type of ranges of temperature. You should have corrosion resistance. Depending on your coolant environment, there are different the scheme of corrosion resistance has to be developed, and should have the sufficiently high radiation resistance for the advanced materials. So to fulfill those requirements, in our lab and our research group, we have developed several different advanced metallic material based on the stainless steel. So we have developed the AS, that is a duplex stainless steel, that are aiming for the application of advanced pure cladding. And we have the called RS alloys. They are having the austenitic structures, but they are having exceptionally high radiation resistance. And also we have the another austenitic alloys, but their compositions are optimized for have the good performance at the high temperature heat exchangers. And there are others, but in this speak, I'm going to talk about mainly this 3 alloy development status. So the first one is ADSS for the light water reactor and the high temperature reactor applications. So this is one of the very damaging pictures for the nuclear industry that happened in year 2011 at the Fukushima site in Japan. Okay. So there are many reasons why this accident has been happened, but the consequences of those accidents has been become much significant because of the hydrogen explosion at that low of the top part of the reactor building. And because of those hydrogen explosion, much of the radioactive material was released to the environment, and we have a significant evacuation in the nearby areas. So one of the reasons why the Fukushima accident became more damaging was the explosion, and that explosion was caused by the hydrogen. And that hydrogen was actually come from the corrosion of zirconium. That zirconium is used as a pure cladding material of water reactors. And the zirconium is known to have a very aggressive corrosion reaction at the relatively high temperatures, like somewhere around the 900 and the 1000 in that temperature. It produces huge amount of hydrogen, and unfortunately, this one is exothermic reaction. So this one is actually a self-accelerating reaction. So after the Fukushima accident, the nuclear industry and the nuclear community was talking about whether there is other better material than zirconium alloys than as a use of cladding material. So the concept of the better cladding material, that is called so-called ATEP materials, the accident tolerant, the pure cladding materials. So there are several different materials has been proposed, and all of them has the excellent high temperature corrosion resistance. So this one is one of the test results showing that compared to the zirconium alloys and the simple stainless steel, many of those proposed material has a very low weight gain. So it has an excellent corrosion resistance. But unfortunately, this one is ceramic, This is coating, so it has limitation. And the metallic material, molybdenum and the picral is known to be poor oxidation resistant, and they have some embrittlement issues. So we try to develop the better material to overcoming those deficiencies. So the idea was that because those materials are basically BCC material, so we try to add aluminum to have a high temperature oxidation, and also to maintain the duplex structures by increasing amount of nickel. So we have the partially austenite and the partially peritic structures, and the alumina formation at high temperature, and we have a better workability and ductile property. Those are these features of developed alloy called ADSS. So this one is the some design scheme. So we have we use the thermodynamic modeling to have the composition like this one, and this one is a microstructure after the several thermomechanical processing, and this one is showing the mixture of austenite and ferrite, and actually there are some small particles called the BIAL phases. So this one is a test result showing the improved corrosion resistance at high temperature. This one is the thermogravimetric test at 1200 degrees centigrade, and this one shows excellent corrosion resistance compared to the conventional zirconium alloys by forming the alumina and the picral, alumina and the spinel structures. And also in the normal PWL environment, they have a slightly positive weight gains. This one is actually more preferable than the weight losses. So if you have weight losses, you have some radiological problem in your primary coolant system. So slight weight gain is a best property in the PWL environment. And also we need to have the high strength material to compensate some of the neutronics issues. So it should have a high strength and a reasonable amount of ductility. So our alloys have a higher strength and comparable ductility compared to the other developed the alloys. And because we have a ferrite, we are worried about the summarizing embrittlement issues. But as I said before, because our ADSS alloy has a certain fraction of austenite phases, so the embrittlement caused by the ferrite was compensated significantly. So we can have a roughly same amount of ductility as the initial material, even though the strength increased because of the summarizing embrittlement. And also, eventually, we produced a very thin-walled tube from the conventional the pilgering process. So we started from this ingots, and then by forging and the pilgering process, and then we produced this about 1.6 meters long and the 3 millimeters thick tube was fabricated. And we are waiting for the irradiation test for the actual power plant application. So next one is RS alloys for the light water reactor and the high temperature applications. This is a modification of the development of RS alloys. So like many other structural materials, stress corrosion cracking is one of the issues for the corrosion resistance material like stainless steel. Especially in the nuclear power plant, we have additional stress corrosion cracking issues called the irradiation assisted SCC. In addition to that, it was known that the austenitic stainless steel has many good properties, but unfortunately, if this austenitic stainless steel is irradiated at relatively high temperature, like 500 degrees centigrade, it actually have the volume changes. This one is called swelling. And this swelling is one of the key determinant property of austenitic stainless steel, and that limit the long-term operation of light water reactor, the long-term use of austenitic stainless steel when there is a huge, large amount of neutron irradiation and the high temperature is expected. So this is a mechanism of avoid swelling, but I think it's better to skip. So the one of the there are several the methods to reduce the swelling and the irradiation embrittlement, because neutron irradiation embrittlement is starting from the formation of the vacancy and the interstellar pairs because of the elastic scattering of nucleus. And then those vacancies are moved around and collected, combined together to form this kind of a void. So the idea is, if you provide enough sink site, enough the defect site, like the great dislocations and the grain boundaries and the precipitate, those vacancies are trapped by those sites, and then they cannot form the large void. So that is the basic idea of irradiation resistance or swelling resistance material. So there are several different methods, but the formation of nanograin, you should have the severe plastic deformation that is not very practical for the large component. And the dislocation in the nanoparticles have some the advantages, but it was not the, it also has a limitation. And for the FMS alloys, the ferritic martin steel and the ODS alloys, it's good, but the ODS fabrication has also fabrication issues. High-depth alloys and the boundaries is currently very early stage for the development. So our idea is that we try to precipitate huge number of the nanoside carbide within the matrix by properly controlling the composition and some mechanical processing, and that provide a significant amount of sink site, so we can have the swelling resistance and the irradiation embrittlement resistance. So this is the photo showing that the precipitation of a huge number of nanoside naive carbide precipitate. And this is the measured data. So we have 10 to the 22nd or 10 to the 23rd number of precipitate per cubic meters. The size is from 8 to 6 nanometers. And we have increase in strength and reduction in ductility, but still we have around 10 or 20% of ductility, so that's not a big problem. So we have a better corrosion resistance. So the key issue of void swelling has to be experimentally confirmed by the ion irradiation. So we have one of the ion irradiation of at the level of 8.5 dPa at the MIT. So this one is comparing the conventional 316 stainless steel and our alloys. So we can see there is a significant reduction of the void side. And actually the volume change of conventional 316 stainless is around 8%, and we are around 1%. So there is about 7 times a decrease in the swelling. But in the advanced nuclear power plant, the amount of neutron irradiation is much, much greater than 8 dPa. We are expecting to have somewhere around 200 dPa at the highest point. So we irradiated the material at 200 dPa. In this case, we irradiated at the Texas A&M. And this one is again comparison of the conventional alloys, and this is our developed alloy. And this is measured volume increases. So compared to the 316, we have around 25% volume increases. We have less than 5% volume increase. So there is a huge difference in terms of the volume change. Also, the degree of embrittlement is significantly reduced from conventional 316, that is 150. So we have roughly less than 50. So this one is also a significant decrease in the embrittlement. I think I'm nearing the end of my talk. So can I have a couple of minutes to complete my presentation? Or should I?
Yes, please go ahead, Professor Chiang.
Okay, thank you. So the third one is the ACEP alloy. This one is for the high temperature application. So we all know that the fossil power industry and also the other power generating industry, the high strength, high creep resistance material is essential to have the ultra supercritical power conversion system, and also the concentrated solar power system. So the target is we should have a creep resistant material, and also that material should have a proper oxidation resistance at that temperature. So this is some kind of requirement shown here. And for that purpose, the aluminum forming alloy has been developed by the Oak Ridge National Lab in the United States that has roughly 20 to 3% nickel, and they added roughly 3% aluminum. So because of those alloying the element, they have the counter prime and also the NIAL B2 phases formation at high temperature. So that contribute the cream resistance. But still, because of those low amount of aluminum and the relatively low amount of chromium, their corrosion resistance is not as good as other high temperature the materials. So our idea is that for the improvement of the high temperature oxidation resistance, we try to increase the aluminum content and also try to add more titanium to have a better cream resistance. But it is well known that the titanium is bad for the high temperature oxidation. So we wanted to balance the amount of titanium and the amount of aluminum to have a balanced creep and corrosion resistance. So we increase both aluminum and titanium together to have the better combination of the creep and corrosion resistance at high temperature. So this is one of the alloys that we developed. So we have roughly 4.5% of aluminum and 3.6% of titanium was here. And this one is a little bit lower content of aluminum and the titanium. And this is a summary of a creep test result of our alloys. So this one is at 750 and 150 degree MPa. So our test alloys have around 500 hours as a creep life. This one is significantly longer than the AFA alloys, but at a little bit lower the loading. So we have 1500, and we have a comparable creep life as other the AFA alloys. So with those the comparable cream resistance, we compare the oxidation resistance. So this is oxidation resistance of one of the alloys we developed, and this is actually comparison of our alloy shown here and the AFA alloys. So in the supercritical CO2 environment, we have roughly 3 or 4 times lower weight gains, and that weight gain becomes even lower when we have a pre-oxidation. Similar weight gains in the steam and the water vapor environment in our data, and this is AFA practice. So we have just a summary of the 3 newly developed alloys for the nuclear power, advanced nuclear power plant application. So this is basically a summary of that I have mentioned. So, okay, thank you. I'm going to stop here. Thank you for listening.
Thank you, Professor Zhang, for his nice keynote lecture. Now I request the audience and participant present here to please interact with Professor Zhang if you have any questions, please.
A quick question, please.
Yes.
In terms of manufacturing, these advanced alloy would be able to be manufactured by typical industrial factories, or a specialization would be needed?
Oh, we developed basically all these alloys by the BIM melting and the hot rolling and cold rolling and the conventional heat treatment process. So this our target is basically utilize the conventional steel making process. We don't have any fancy fabrication process. So it can be baked into tons or 10 tons of scale.
Thank you.
Professor Chiang, I have one question. We know that good cladding material require low neutron absorption capability. So what is your take for the materials you have developed for cladding materials?
Yeah, that is actually good question. We know that the zirconium has a very low neutron cross section. Okay, but we add nickel, and also we have iron and chromium, so they have a fairly large amount of neutron absorption cross section. So the idea is that to compensate those absorption cross-section differences, you have to make the cladding thickness decrease from current 0.5 millimeter to 0.3 or 0.35 millimeters. But if you wanted to decrease the thickness, you have to increase the strength of the material, okay? And also should have a certain ductility. So this is the reason why we favor have a high strength material and also having certain amount of ductility. So the thickness became smaller, and you have a little bit bigger pure pellet within those cladding material.
Okay, thank you, Professor Zhang. Is there any more questions for Professor Zhang? If not, then I must thank Professor Chiang from Korea Advanced Institute of Science and Technology for delivering a nice keynote lecture in session 8 of ICEP conference. Thank you, Professor Chiang. Now we'll start the contributed papers. So our first paper is paper ID 18, which will be presented by Ms. Pyangsakul Yodchumpu from Chiang University, Thailand. So, is the presenter ready for the presentation? Yes, please unmute yourself. Please start.
Hello, my name is Pyangsakul Yodchumpu from Energy Technology Environment Research Center, Department of Mechanical Engineering, Faculty of Engineering, Chiang Mai University, Thailand. Today, I will present my research toward low carbon community greenhouse gas emission reduction project in soil wastewater treatment. This project focuses on the reduction of greenhouse gas emission from soil farm, resulting from reducing biogas from the wastewater treatment. The outline has 4 topics: background on biogas project, greenhouse gas emission reduction mechanism, results of greenhouse gas emission, and conclusions. All topics are mentioned in the following section. This research work focuses on the reduction of greenhouse gas emission from the anaerobic wastewater treatment process from soil farms to produce biogas, preventing greenhouse gas from entering the atmosphere. 3 biogas plants were built in 3 different provinces in Thailand. The first biogas project consists of 3 soil farms with total capacity of 400 square meters of biogas built at Tha Dinh Dam Sub-District, Chai Badan District, Lopburi Province, supplying 130 households. The second project has capacity of 300 square meters of biogas built at Tau Pun Sub-District, Song District, Phra Province, supplying 188 households. And the third project consists of 3 soil farms with total capacity of 600 square meters of biogas built at Ban Uom Sub-District, Mueang District, Lampang Province, supplying 252 households. Not only these projects help the reduction of the release of methane to atmosphere, but they provide biogas to households in nearby communities for cooking fuels in the replacement of LPG at the same time. Biogas is renewable energy source, which is produced by anaerobic digestion of wastewater from soil farm. Biogas consists of methane and carbon dioxide. The reduction of greenhouse gas emission depends on how much the methane can be contained. The calculation methodology for greenhouse gas emission reduction from the methane recovery in swine wastewater treatment is based on the calculation guideline from Thailand Voluntary Emission Reduction Program, or TWER, that provided by Thailand Greenhouse Gas Management Organization, or TGO. Calculation methodology used in this project is TWER MED WM0H version 2, named Methane Recovery in Swine Wastewater Treatment. And the detail of this methodology is shown in the table. This methodology includes the calculation of greenhouse gas emission in the base case assessed from the degradation of volatile solid from swine farm wastewater by anaerobic wastewater treatment process. Greenhouse gas emission involve baseline emission, project emission, and leakage emission. About equation, baseline greenhouse gas emission is merely calculated from methane emission as a result of the degradation of volatile solid by anaerobic wastewater treatment process in swine farm. The number of rice pigs were recorded by farm owners. The global warming potential and other parameters are assessment from SS report of IPCC. And project emission is calculated from the amount of carbon dioxide released from burning fossil fuels, use of electricity, and the leakage of methane from the storage system. But this project, fossil fuel was not used in operation and no greenhouse gas emission from biogas leakage occurred in the project. Therefore, this parameter and this parameter is are equal to 0. So emission reduction is calculated from this equation. Results of greenhouse gas emission in project 1. Only methane emissions from the degradation of volatile solids from pig farm wastewater by anaerobic wastewater treatment process is considered in calculating greenhouse gas emission for the baseline emission. Carbon dioxide emission from electrical energy from the biogas pumping and the leakage of methane from the storage system are used in calculating greenhouse gas emission for the project emission. And there is no leakage of greenhouse gas emission outside the project boundary. We found that the project greenhouse gas emission reduction certified in 2020 by TGO is 1,716 ton carbon dioxide equivalent, which is 2.57% higher than expected greenhouse gas emission reduction due to the increase in number of rice pigs during the greenhouse gas emission reduction certified year. Same as project 1, in project 2, we found that the project greenhouse gas emission reduction certified is 658 ton carbon dioxide equivalent, which is 15.23% higher than expected greenhouse gas emission. And in the project 3, the project greenhouse gas emission reduction certified is 816 ton carbon dioxide equivalent, which is 14.73% less than expected greenhouse gas emission reduction. In the conclusion, total certified greenhouse gas emission for greenhouse gas emission reduction for these 3 swine farms is 3,190 ton carbon dioxide equivalent. The amount of greenhouse gas emission reduction depends largely on the number of pigs that are actually raised in the farms. The amount of greenhouse gas emission reduction depends mostly on the number of pigs that are actually raised in the farm and reliability of the biogas system in the plants, such as pumping system and biogas storage. Data must be recorded regularly and accurately using the current instruments in accordance with calculation details written in a project design document to ensure the accurate calculation of the emission reduction of greenhouse gas. Maintaining a training program on greenhouse gas emission reduction calculation, measuring instruments, and doing monitoring reports must be carried out to people involved in the biogas project. And the collaboration and wellness between farm owners, workers, and local administrative organization play a vital role to the success of becoming the low carbon community. I have finished the presentation. Thank you for your attention. And for more information, please contact this email. Thank you.
I thank you, the presenter, for presenting a nice topic on carbon greenhouse gas emission reduction. Now I request the attendees to please interact with the presenter. Any questions for the presenter? Professor Nakon, do you have any questions for the presenter? Okay, then I have a question. So, what type of biogas plant you have installed for your study? What technique you have used to install a biogas plant?
Sorry, I can't catch that. Please ask me again. Please. Sorry.
Which technique you have used to develop biogas plant for your study?
Cover lagoon, yes.
Do you understand my questions? Or I request Dr. Nakon to please. Okay, thank you, the presenter, for your nice presentation. You have delivered the presentation within the time specified. Now I request presenter for paper 32, Mr. Parin Khongkrapan, Mr. Parin Khongkrapan from Chiang University. So I request Mr. Parin Khongkrapan from Chiang University to please share the presentation. I request a presenter for paper RD 18 to please answer your presentation.
I think Kun Yong Yut will do presentation for this one.
Yes.
Okay, Yong Yut, go ahead.
Yes, good morning, everyone. I'm going to present my video. You can share on the YouTube. Can you hear me?
Yes, please go ahead.
Yes. Can co-share share my video?
Yes. I request the co-chair to please do the necessary formalities so that you can see the videos available on YouTube.
Yong Yut, can you share your file from your computer?
Computer.
Can you share it? Can you share the file, please?
Yes. I'm not sure because the sound is not loud or not.
Okay, let's try.
My name is Did you hear it?
Yes, very good.
It is audible.
Metro University, Chiang, Thailand. Today, I would like to talk about the energy efficiency enhancement of a hot air food dryer with equivalent waste heat system. This presentation consists of three main parts. The first part is introduction. The second is materials, and methods. The last part is a result and conclusion. Okay, let me move to the first part. Drying. The drying is one of most essential techniques for improving food quality, extending cell life, and potentially increasing market price of agricultural products. However, relatively high energy consumption during drying process of hot air dryer is increasing production cost. So it is estimate the drying process consume about 60% or more of total energy necessary for food processing and manufacturing. The waste heat is responsible for most of the energy lost. In the drying process, as the hot and moist air is directly evacuated from the drying chamber. It is a matter of economic urgency to design and develop energy-saving equipment for traditional food dryer. Waste heat recovery technology is an efficient tool to reduce energy consumption and is widely used in the food industry. So, in this research, a cross-flow heat exchanger was designed and implemented in a semi-industrial food dryer and to starting and to finding give energy consumption and dryer efficiency were evaluated compared to traditional dryer. Material and methods. The dryer have a performance of 10 kilowatt and of approximately 1 cubic meter drying chamber, about 1,000 tube with a dimension of 0.15 meter. Designing of a cross-flow heat exchanger, you can see on the picture. This is a exhaust in, there's a exhaust out. This dry air in and dry air out. The heat exchanger was composed of food grade stainless steel FUS 304 with a thickness and thermal conductivity of 1 millimeter and 15 watt per meter Kelvin respectively. About external dry air enters the heat exchanger by 10 centimeter diameter tube. Flow applause, correction of failed exhaust pipes, each with a diameter of 5 centimeter and a length of 60 centimeter. And you can see on diagram. This is diagram of this experiment. You can see the position of a heat exchanger on the top of dryer. The water, 1,000 grams of water in container was placed, and the center of drying chamber, which functions as the drying load. Drying temperature was set to 100 degrees Celsius. About exhaust air velocity at the heat exchanger outlet was adjusted to around 1.0 meter per second, and mass flow rate is 0.017 kilogram per second, and 1.5 meter per second. And mass flow rate is 0.025 kilogram per second. And the last condition is 2.0 meter per second, and mass flow rate is 0.033 kilogram per second. That's a maximum capacity of this dryer. To experiment for 1 hour, temperature at different place, and dryer electrical power consumption per measure every 5 minutes. At the end of the test, the water container was weighed to determine the amount of water evaporate during the drying process. And you can see on the graph, we found that drying chamber temperature of both dryer were not substantially different because the used heat exchanger did not increase the heating rate. So the drying rates were not significantly different, with about 0.6 to 0.8 kilogram water per hour, depend on exhaust air flow rate. And the heat exchanger, when operated with different drain exhaust rate, lower exhaust air temperature by almost 33, 23, and 22%, and raise intake air temperature by about 31, 34, and 49% respectively. The addition of a heat exchanger reduced the dryer overall electrical power consumption about 14%, 22%, and 24%. And it reduced waste heat from the dryer by around 25%, 37%, and 49% respectively. The energy efficiency of the dryer was increased by 14%, 24%, and 28%. And in terms of SMER by about 14, 24, and 28%, and 11%, 19%, 22% for SEC. So the conclusion of this research, you can see on the table, the efficiency and effectiveness of the heat exchanger measurement at about 47% and 51% respectively. The electrical power consumption of the dryer was reduced by 0.71 kilowatt-hour, which account for an energy saving of almost 24%. When installation of the cross-flow heat exchanger was found to enhance the temperature of the dryer intakes air by approximately 35% and the dryer efficiency by more than 28%. Thank you for your attention.
Yes, thank you, everyone.
Thank you for your presentation. Now I request the audience present here to please interact with the presenter. If you have any questions for Mr. Pari.
Yes.
Okay, I have any question.
Yes, please.
Okay. Mr. Yongyut.
Yes.
Something that's called the cost of construction of your dryer.
In cost.
The cost of.
Cost of that this dryer is almost 100,000 baht.
It's okay. Thank you.
Yes.
Is there any question? Any further question? One question from my side to the presenter. Have you calculated the economic analysis? Have you done the economic analysis? With annual cost savings and that needs to be compared with the investment and whatever you have spent for adding this waste heat recovery system that must be recovered from your savings. So have you done this kind of elaborate cost calculation? If not, then I suggest you to please go for this elaborate cost analysis. It would add the value to your work. So nice work from the presenter of paper ID 32. Now,
Yongyut, have you done economic calculation?
Yes. I have done, but it's not in this paper.
Okay.
Okay.
Don't worry.
Thank you.
Excuse me.
Yes, please.
100,000 is just the dryer cost, but the heat exchanger cost is just about 6 or 7,000 baht. Just only 6 or 7,000 baht.
Okay.
Yes.
So now I request Miss Nuttida Changhom from Chiang Mai University to present his paper ID 40.
Thank you.
Yongyut, stop share. Yongyut, please stop share from your side.
Okay.
Make it full screen.
Okay, Natida, please start.
Presenter, Miss Nuttida, can you hear me? Is there a problem with audio?
Natida, are you okay? switch on the mic, please. Unmute.
Yes. It's still muted. She is muted.
Nathida, can you unmute? We cannot hear you.เกิดอะไรขึ้น
ค่ะขออนุญาตค่ะมันเปิดแล้วมันเด้งออกอะค่ะซูมอะค่ะไม่สามารถโชว์ขึ้นมาให้ทำเปิดนิวอะไรได้เลย
ตอนนี้คือคุณแชร์ไฟล์ได้แล้ว
แชร์ได้แต่ว่าคือพอดีว่ามันไม่สามารถเปิดขึ้นมาให้เห็นให้เปิดนิวได้อะค่ะ
งั้นปิดแล้วเปิดใหม่ไหม
ลองได้ค่ะลองเข้าใหม่ใช่ไหมคะ
ใช่
อาจารย์เน็กให้คนอื่นก่อนไหมคะ
ได้Chairman.
Yes, please.
Mr. Chairman, Nathida seems to have a problem with her connection, so
okay.
she would like to present after the can.
Okay, no problem.
The next
no
one.
problem.
She will disconnect and come in again.
Then I request the presenter of paper ID 49, Miss Pimpod of Chiang University, to please present her paper. Now, Miss Nathida must unshare her slide.
Hi, I am Pimpod Pibun.
Nathida, can you stop sharing the file first? Pimpon, can you share the file now?
I can share my screen.
Okay, hold on. You try, okay?
Okay.
So, do you see video?
Yes, thank you.
I am Pimpon Pibun from Energy Technology for Environment Research Center, Chiang Mai University, Thailand. I will present greenhouse gas emission reduction in refuse-derived fuel production from municipal solid waste. The outline is 4 topics. There are background on RDF projects, greenhouse gas emission reduction mechanism, the result of 2 RDF production plants, and conclusion. The background. This research focuses on the greenhouse gas reduction emission from anaerobic process in landfill by produced RDF. 2 RDF production plants were built in Sisaket province in Thailand. The first RDF project is in Sisaket municipality with capacity of 87 tons per day. The second RDF project is in Khun Han sub-district municipality with capacity of 20 tons per day. New Delhi municipal solid waste within the municipality and nearby in 200 kilometers were used. The greenhouse gas emission reduction mechanism. RDF is produced by mechanical and biological treatment technology. In the fermentation process, bacteria decompose organic matter in the waste. The mechanical process, the pile reverse to achieve better biodegradation process and prevent methane from anaerobic digestion. After that, sieving the waste to separate the organic matter as soil amendment, and finally RDF. The reduction of greenhouse gas emission depends on how much the methane can be contained from the degradation of volatile solid waste by anaerobic process in landfill. The emission reduction can be calculated by the methodology which directed by Thailand Greenhouse Gas Management Organization or TGO. Calculation methodology used in this project are Tier 2 waste 01 for calculation of greenhouse gas emission. In the base case, assess from degradation of volatile solid from the waste by anaerobic process in landfill, and Tier Met WM04 for calculation of greenhouse gas emission. In the project case, assess from carbon dioxide emission from burning fossil fuels and electricity consumption produced by burning fossil fuel in the project, and sometimes methane emission from fermentation process. Greenhouse gas emission involves baseline emission, project emission, and leakage emission. The baseline emission the baseline emission equation is given by equation 1. The equation aggregate quantity of the waste to be eliminated by other means instead of landfill, multiplied by proportion by weight of woods, papers, foods, textiles, twigs, and leaves, and multiplied by correction factor according to the methane correction factor, which based on the type of landfills. The project emission equation is given by equation 2. The equation aggregates the emission from the use of fossil fuel and electricity, sometimes from anaerobic wastewater treatment process, in unit ton carbon dioxide equivalent per year. The emission from fossil fuel consumption is given by equation 3, which aggregate of the amount of fossil fuel consumption and net calorific value with emission factor from burning fossil fuel. The emission from the electricity consumption is given by equation 4, which aggregate of the amount of electricity consumption and emission factor from electric generation in the grid system. However, there is no municipal solid waste transportation more than 200 kilometers. Therefore, leakage emission can be neglected. The result of greenhouse gas emission. The result of Project 1, RDF production from municipal solid waste by Sisakhet municipality in Sisakhet province, was certified in 6 months from July to December 2020 is 3,956 tons carbon dioxide, which is 54.8% less than expected. The result of Project 2, RDF production from municipal solid waste by Khun Hàn Sub-District municipality in Sisakhet province, was certified in 12 months from January to December 2020 is 657 ton carbon dioxide, which is 42.5% higher than expected. The conclusions. The total certified greenhouse gas emission reductions for these two RDF projects are 4,613 ton carbon dioxide. The amount of greenhouse gas emission reduction depends on the quantity of municipal solid waste to be eliminated by RDF project and proportion by weight of volatile solids. Zhejiang municipal contribute much more greenhouse gas emission reduction because of bigger administrative area, resulting in more collection of solid waste. Required data and documents must be recorded using calibrated instrument according to calculation detail provided in project design document to obtain the accurate amount of greenhouse gas emission reduction. And the collaboration between workers and a local administrative organization is the key to the success of the reduction of greenhouse gas emission. Thank you for your attention.
Thank you, the presenter. And now I request the audience to please engage with the presenter with some questions. Do you have any questions?
A quick question from me, please.
Yes, please. Carry on.
Pimpon, you mentioned collaboration between worker and admin people. What do you mean that is important? Are they happy with the RDF work collaboration reduction of CO2, or what are their reaction when you go and do the work with them?
Can you ask me again?
When you work with the people in municipality, how did they react? Are they happy working with you, or?
They are happy and very welcome.
And collaborative, you mean?
Yes.
Okay.
Thank you.
Is there any questions from the audience? If there is no question, then I should thank the presenter for his presentation. Now I request the presenter for paper ID 111, Mr. Padin Khonkrapan from Chiang University. Mr. Padin, could you please share your slide? I request the earlier presenter to please answer the slide.
Dr. Parin, who is presenting the next?
Mr. Pibun.
Oh, okay. Mr. Pibun, can you please?
Yes.
Go ahead and share your video file.
Yes, I'm going to open my video presentation. Hi everyone, let me introduce myself. I am Pibun Sikham from School of Renewable Energy, Metro University. Today, I am going to talk about performance assessment of hot air First dryer with infrared heating system. And begin with introduction. Drying or dehydration is an essential technical in food processing and preservation process. It is used to remove water from product in order to discredit microbiological activity and dismiss physical chemicals such as drying storage. The humidity should be below 12% with standard. Most use hot air temperature 40 and 70 degrees Celsius. And choose the air circulation as 1 to 2 meters per second. Facing the incident is that it takes a long time today. Therefore, infrared radiation is set, which can reduce the drying time by up to 50%. An original hot air dryer in the reserve hot technique and approximately 5 millimeter drying chamber. There will 10 sequence drying tasks with a diameter of 90 centimeters. All drying tasks can be rotated as the summer rotation speed is the rate of 1 to 10 respiration per minute. For drying performance assessment methodology and reference lamp was introduced as a displacement of 20 centimeters. Begin with experimental setup. The objective of the experiment was to evaluate the performance of original hot air dryer to complete its with modified version by ASEP the infrared heating system. This leads directly to my next point. The experiment used 10 kilograms of copper lining. The standard installed humidity is 60% weight. Dye with hot air is 45, 55, and 65 degrees Celsius. Compared to the use of hot air combined with 300 watts of infrared at the same temperature and with speed. Begin with result and conclusion. From hybrid drying, the drying time was reduced to 200, 120, and 110 minutes. When operates with hot air temperature 45, 55, and 65, lending to time serving to about 70, 67, and 49% respectively. The hybrid system has a higher as-well drying rate. That's the ordinal quantitative dryings by 230, 200, and 145%, which refers to converting hot air is worse fun. That's the modified dryer operated. Is hybrid most produce chemical is dehydrated, careful lighting. Infrared heating was forced to improve the energy efficiency of the dryer from 40.21 to 36.11%, from 30.03 for 40 50.55% and from to 50.51% for 45, 55, and 65 respectively. From detailed result was found that about 10 goods produce purified goods with modifiable difference in drying time, energy, efficiency, and product quality. Higher process temperature produce the final discharged cover diary with most bold color and keep fitted that has lower market price. This moment of influence, eating with traditional hot air converted drying significantly is proof the drying performance reduce the process time and energy consumption. In the case of 65 hot air combined with infrared 300 watt, the maximum energy efficiency of the dryer was less from about 60 to 54%, with reduced drying time and reduced over power consumption by 17%. The optimum hot air temperature for the high-vis drying the crude. When says high dryer performance and produce high product quality should not be about 55 Celsius as this condition the modified dryer needed only about 100 min to product. The highest differentially with acceptable moisture content and water activity version. Begin with environment. This was partly supported by the Thailand as Agricultural Research Development Agency, National Research Council of Thailand, Metro University, and Chiang Mai University.
Presentation is over. Now I request the presenter to please take up few questions from the audience. Audience, if you have any questions. I have
some question. Mr. Pipun, this the cruise project. I have some question. Your infrared in your system use energy from electric or LPG?
Electric heating.
Oh, okay. And some question. How much the cost of construction hybrid system?
Please, Dr. Brian, answer with the question. Please, Dr. Brian.
Excuse me. This is a project of me. This system consists of the intelligent control. Almost of the money that we spend to this project is about 1 million baht.
Oh. Okay. Thank you.
Thank you.
So, thank you, the presenter, for your presentation. Now there is a paper left. I think it is a submission ID 40. And the paper was to be presented by Ms. Nutida. So, is she available? for the presentation?
Thank you.
Oh, okay.
Yes. Please start.
Good morning, ladies and gentlemen. My name is Nathida Chanhom. I come from Faculty of Engineering Chiang Mai University, and today I would like to present biomass to biofuel precursors, conversion of glucose and fructose to 5-hydroxymethyl by acid hydrolysis, and co-research Miss ประภาพร ประเสริฐพงษ์ and Professor นครทิพยวงศ์ In recent years, biomass is rich with biorenewable energy sources such as woody biomass, straw, and agricultural materials. Biomass is available in large quantity in many regions, and the production of organic chemicals because of its abundant renewability and wide distribution. If one considers the possible downstream chemical processing technology, the conversion of sugar to value-added chemical is very important. For example, biomass derivative conversion to plastic, to ethanol, and other. Why should signal biomass feedstock because the first, in Thailand, biomass is abundant. The second has high cellulose content, and it also high pollution and harsh environment, and biomass reduce competition with fuel cost, and its family can be go around. Bio-based economy and biorefinery and trade. In this sense, biotechnology plays an increasing importance on key industrial sectors in the production of the commodity and specific products for the utilized, including fuels such as ethanol, biodiesel, and BTL, and energy, heat stream, electricity, and chemical, commodity, and specialty, and materials, bioplastic, and biomaterials, such as in this biorefineries are continuing to work, and in recent we are interested for research from lignal biomass, bio and refinery towards bio-impact biological resource materials, so called bioresource, dealing from living matter and the world. Refineries typically occur the conventional term derived from the petroleum-based refining process system. Biorefinery have bioethanol, biodiesel, bioplastic, biochemicals. In this world, we are interested experiment conversion sugar to biofuels and called DMF. The objective was to investigate the conversion of glucose and fructose to HUF and as an intermediate of the producing DMS by the acid hydrolysis reaction. Length of the acid concentration time at peak temperature will be the average the order to obtain the highest yield of HUF. This slide shows us pathway of GMF preparation from biomass. The process is a pre-process conversion of biomass to DMF. The first pretreatment The second hydrolysis from fructose, sugar, and glucose use dehydration process, and HMF, 2DMS use hydrogenolysis process, respectively. The slide shows us overview methodologies, biomass, lignocellulosic biomass, 2DMS, pretreatment, enzymatic hydrolysis, and dehydration, and next in the future of research, hydrogenolysis process, conversion of HCl to MS. In this work and presentation now, I present conversion of sugar to HMS by dehydration process, conversion of sugar HMS by hydrolytic catalyst. In this and design experimental by CCD is have to factorial time and concentration at stable temperature 140 degrees Celsius. The slide shows that experimental procedure for dehydration for sugar to the HMF. In this work, to type sugar, including glucose and fructose, and the first step, concentration of hydrate hydrocolloids, 20 milliliters into an ml flask, and next mix with 20 milliliters of sugar, glucose, and fructose respectively. And after that, heated in an autoclave at 140 degrees Celsius for reaction time 30 to 40 minutes, and it was then sampled and injected into the high performance liquid chromatography for analyze HMF respectively. The slide shows us the methodology for design experiment, use central capacity design. Table 1 shows length and coded level of the process variable. It has two factors, time sample x1, length 30 to 40 minutes, and concentration sample x2, 1.65 to 4.95 percent weight by weight, and a fructose glucose ratio weight by weight 33.3 grams per liter at current temperature 140 degrees Celsius. The results show that table 2 is a design experiment by CCD. The experiment results from the testing 12 conditions for the statistic for HMF produced from glucose. The HMF condition from glucose length from 49.8 to 67.1% at up on the condition for experiment. It was found that the acid concentration of 3.3 and 35 minutes of the time operation is the optimal condition, highest yield of HMF, and for experiment run 9 to 12. I focus with pre-repetition for the experiment. It was found that condition 9 to 12 with HMF of 67.1, 66.8, and 66.1 and 66.3 were as a result experiments, and This can compare with the simulation of CCD technique. Yield HMF 66.57% respectively. The slide show that the table shows us is what found the similarity between the predict and experimental value was the event from the very small error, and its HMF version process was optimization to the highest HMF conversion from glucose using ASEP. Average using ASEP and experiments 66%. And next, result and discussion, experiment design and response of HMF from fructose. 12 condition, it was found that run 9 to 12 at 35 minutes at a concentration 3.3% respiratory. It was found as high yield as a 76.16, 75.8 and 75.9 respectively, and compared with the simulate of the CCD. Condition 9 to 12 yields HMF 76.9%. The result showed us the HMF conversion from fructose was found linked to the 60.8 to 76.1 depend on the condition of experiment 2. It is analyzed. ANOVA was applied. It's a model. It's showed us is significant of the process parameter of the HMF conversion, and as R2 R square and 2 square adjust for the conversion model were 0.7255 and 0.02467 respectively. And conclusion, the research. There are 3 factorials to factor in the converting glucose to 5 hydroxy methylfurfural or HMF by dehydration and acid concentration at time at the temperature is both high yield at the condition concentration 3.3% weight by weight and the time of selection at 35 minutes and it was HSU of the average 67% from glucose and 76% from fructose respectively. Thank you. I would like to thank National Research Council of the Thailand and Chiang University and Zhejiang University of the Technology Technology, the Professor Dr. Nakornchip Phayawong. Thank you for your attention.
Thank you, Ms. Notida, for your presentation. Now I request the audience to please ask a few questions if you have any questions or doubt to the presenter. Do you have any question? So I have a question, like it's a wonderful research done by Ms. Nutlida. My request is whatever biofuel you are proposing, have you calculated the calorific value? Have you measured the calorific value of that biofuel?
Again, please, Mr.
Have you calculated the calorific value of your liquid product?
Approximate 20 milliliters and is mean analyze or the experimental experience. Mr. Nakhon.
Do you have the number for calorific value of your liquid product?
In the project, in the research, we are interested to liquid product, but analyze have other liquid more to liquid. Yes.
Okay.
We have not done the calorific value determination yet.
Okay, thank you. So all the papers are presented. I thank our conference chair, Professor Nakhon, and my co-chair for this session, Dr. Kritikon Sasujit, and all the presenters.
I would thank you, Dr. Paul, for sharing the session.
Nice.
And for those who participate, maybe you can open your video so that we can do group photo.
So it's a nicely going organized conference going on.
Thank you. Okay, we can do a quick group photo for everyone.
Yes.
You can send photo to your mom and dad that you've done presentation already. Okay. Not everyone is here. Okay. Our keynote speaker is still with us. Yes, thank you very much. Okay, I think we do the caption. Some of this photo and the live your presentation will be in our official website. Dr. Harun will put the YouTube for those who wish to see it again. Okay, now I thank everyone for participation and thank the session chair again, Dr. Paul, for helping us. I think we will have something like less than 15 minutes to go for the next session. We have 15 minutes for lunch, and then our session will start again at 12 o'clock Thailand time. Thank you everyone.
Thank you everybody.
Thank you, Professor Chiang.
Thank you.